Welcome to the ChemDoctor, and this is the second video in the series on the aldol condensation. Make sure you see video number 1 that outlined the aldol addition, where we have the combination of two aldehydes to form what's called an alpha-beta hydroxy carbonyl molecule. Now, the only difference between an aldol addition and an aldol condensation are the conditions. So you'll remember from the addition video that we utilize sodium hydroxide as our nucleophile in water, but the difference is that we didn't do any heating. So if the same reaction is carried out under similar conditions except we heat the mixture, then what ends up happening is the hydroxyl group that would normally form in the addition is actually going to be lost in the form of an elimination as water. And that's one reason why we call the aldol condensation a dehydration reaction, because water, the hydroxyl group is going to be lost as a water molecule. Now the viewer may be confused by the use of the word condensation and dehydration in the same definition. So you need to just realize that in organic chemistry, when we talk about a condensation event, we're talking about taking and coupling two large molecules via a covalent bond, which happens in the aldol addition, because we're bringing in two of these aldehydes and we're forming a new carbon-carbon bond, making the molecule larger. And it's called an aldol because we end up producing both a carbonyl and a hydroxyl group in the same molecule. If we heat the mixture, then what ends up happening is we lose the hydroxyl group as a water molecule, and therefore we say a dehydration is occurring within this particular condensation reaction. Just remember that the word condensation is being directed at bringing the two molecules together to form a larger molecule, and the dehydration is in reference to the fact that we're going to lose a water molecule in that process. Now, let's go ahead and get started, and remember that an aldol condensation is going to involve an aldol addition. So I'm going to take you through the entire mechanism. Remember again that hydroxide is actually going to be the initial nucleophile that's involved in the reaction. All right, and the hydrogens that I show in our aldehyde here are acidic because of the electronegativity difference between the oxygen, the sp2 hybridized oxygen in the carbonyl itself. And so there's a partial negative charge here. And in this video, I'm going to leave the electrons off the oxygen. I'm going to assume that the viewer can sort out the fact that they're there. It will just make it more efficient for me. This particular carbon is also partially charged with a partial positive charge, and the electronegativity transmits this electron withdrawal across these covalent bonds. So these hydrogens that are in the alpha position are actually acidic, meaning that they can, with an appropriate nucleophile, be removed from the molecule. So in the very first step of the mechanism, hydroxide is going to come along and it's going to abstract one of these protons. The result is going to be that the electrons that were in this covalent bond are going to move into this position between the alpha carbon and the carbonyl carbon, and the electrons that belong to the double bonded carbonyl are going to shift onto the oxygen. The net result is we end up forming what's called an enolate ion that is resonance stabilized. So I'm going to go ahead and draw that here. Here's the double bond. The oxygen now has a negative charge on it because it's got 3 unshared pairs of electrons. Here's the aldehyde hydrogen. And then we're going to have, I'll put our methyl group back, and the other hydrogen that's here. This is in a resonance relationship with another molecule. So keep in mind that a pair of electrons on this oxygen can shift back down or delocalize back onto the carbonyl carbon, and that's going to force a set of pi electrons here onto the alpha carbon. So to indicate that, we'll go ahead and draw that structure here, and I'll put my methyl group back, and then we're going to have a hydrogen, and then the carbonyl carbon with the double bonded oxygen again, and we'll have our aldehyde hydrogen. All right, so this is the enolate, the resonance stabilized enolate, ions. All right, let me just fix that. All right, resonance stabilized. And now what's going to end up happening is we've generated basically, and I talked about this in the other video, this particular carbon is an anion, a carbanion to be specific, and it can operate now as a nucleophile. Okay, so to show that situation, I'm going to move it out of my brackets here, and I'm going to redraw it. I'm going to put my pair of electrons down here so that the mechanism is absolutely clear to the viewer. Okay, and we're going to have another of the two molecules, and I'll put this one adjacent. Okay, and that's going to look like this. All right, and remember, I just want to be abundantly clear here. This has got a partial negative charge on it, and the carbon is partially positive, so it's electrophilic. I'll put a label on it. All right, and this set of electrons is going to interact with the carbonyl carbon, and we're going to now have now have another molecule. So let me go ahead and I'll draw that below here. Okay, and what that's going to look like. And don't be confused. What I did was I turned the molecule around. I need my carbonyl hydrogen, or the aldehyde hydrogen back. Let's see, and then we're going to have CH2CH3 here. All right, so now we have this new intermediate, and let me go ahead and label. So this is the alpha carbon here, and this guy here is my beta, is the beta carbon. And remember, for the addition reaction, we can have a pair of electrons that are on the enolate oxygen, abstract a hydrogen from water, and in that case we're going to end up with our alpha beta hydroxycarbonyl compound. All right, so from the addition reaction, this is what this is going to look like. And we need to get to this point because in order to understand the elimination, we have to start with this. Okay, now this hydrogen right here, don't forget, is acidic, and the reason it is because it has a relationship to the sp2 hybridized oxygen, which is here, and oxygen being electronegative, and on the other side of it we have an sp3 hybridized oxygen, which is also electronegative. So this hydrogen is acidic. Okay, so what can happen, and it's going to be more likely to happen when you're heating this reaction because of the extra kinetic energy that's being introduced into this system. So we can have a hydroxyl group. Let's see, I'm going to change my color for that. We can have a, excuse me, what I said was hydroxyl, I meant hydroxide. All right, and it can make a nucleophilic attack on this hydrogen. So it's going to abstract it, and that's why I say one of the products out of this is going to be H2O. All right, and that's where the dehydration event is coming from. And the result is that this set of electrons can come in here like this. And the hydroxyl group is going to be eliminated as hydroxide. So let me show that moving off over here. So we're going to have OH minus that is eliminated off of the molecule. All right, which can interact with water as well to be protonated. The net result is going to be a new molecule, and here's what it's going to look like. So here's my aldehyde back. All right, and then we're going to have, here's my methyl group, and we end up with a double bond here. Whoops, I need to come back to the molecule that is above here because I left a hydrogen off. Sorry about that. All right, so we have a hydrogen here. And then we have the methylene and the methyl group here. So you can see, let's see, 1, 2, 3, 4, so everything's good. All right, and now this has become an alpha, beta, unsaturated carbonyl. All right, now I hope this helps the viewer that asked specifically for the video. I know that you also asked for the Clayson, and I'm going to deal with that in a separate couple of videos. All right. I would like to thank the viewers for taking the time to watch my presentation. You can find more videos at www.chemdoctor.org. Thanks again for watching, and I'm going to go ahead and sign off.